Section 3.2 continued. In the previous section on 3.1, we learned how to solve systems of equations by graphing. Then at the beginning of section 3.2, we learned how to solve systems algebraically. And in that part, we learned how to solve them by substitution. Now we're going to continue in section 3.2. We're going to use algebraic methods again, but this time we're going to use the elimination method. To use the elimination method, we need to get the variables on the left side of the equation, and we need them in alphabetical order. Number two, we need to stack the equations on top of each other so that the common variables line up vertically. Number three, if needed, we need to multiply one or both the equations so one of the variables' coefficients are opposites. We will demonstrate that. That will make an equivalent system. That means linear systems that have the same solutions. Number four, we want to add the equations vertically. Number five, one of the variables is eliminated. Solve the remaining variable. And six, substitute that solution into step 5, one of the original equations, and solve for that variable. Let's take a look at an example. We want to solve each system by elimination. So you'd have this sample, and from your book you would copy them. A minus B equals a negative 14, and A plus B equals a negative 4. Now, in this problem, we already have both variables on the left side of the equal sign. Also, those variables are in alphabetical order. Now, all I need to do is to determine if my coefficients are opposites. If that's true, then I can just add these two equations vertically, and then one of those variables will drop out. Here, this is a positive 1 and a positive 1 in front of my A. If I added that, that would give me 2A. I need to have them drop out. For the B's, I have a negative 1 and a positive 1B. If I added those, that would give me a 0B, and the B would be eliminated, leaving me only an A. So this makes this problem easy because I already have opposites for one of my variables. So all I'm going to do is add them vertical. 1A plus 1A is 2A. My B's will eliminate because when I add them, a negative 1 plus 1 is 0, and that equals a negative 14 plus a negative 4. That gives me a negative 18. Now I have a simple equation that I can solve. I just divide both sides by 2, and I get A equal to a negative 9. Now I take this value for A and substitute into one of my original problems. It doesn't matter which one I use. I'm going to use the bottom one. A is a negative 9 plus B equals a negative 4. Now I just add 9 to both sides, and I get B equals a positive 5. Therefore, my solution is A equaling a negative 9 and B equals 5. My next sample for elimination. Here I have 3y equals a negative 5 minus 2x. I'm going to add 2x to both sides to get my variables on the left side. That's going to give me 2x plus 3y equals a negative 5. And I have them in alphabetical order. And then I have my other equation that has my variables already on the left in alphabetical order. So I'll just bring that one over. 7x minus 3y equals 23. The first thing I want to do is to see if I have any like variables that the coefficients are opposite. If I do, then all I need to do is combine these two equations. 2 and 7 are not opposites. Here, a positive 3 and a negative 3 are opposites for my y variable. So all I'm going to do is to add these vertically. 2 plus 7x is going to give me 9x. Positive 3 minus 3 eliminates my y variable, leaving me with only one variable to solve for. And when I simplify the right side of my equation, I get a negative 5 plus 23. That will give me a positive 18. On my equation, I'm going to divide both sides by 9. And my solution for x is 2. Now I just take that value for x and substitute into one of my equations from the beginning. Here I'm going to use the top equation. That gives me 3y equals a negative 5 minus 2 times 2 when I substitute in for x. That gives me 3y equals a negative 5 minus 4. 3y equals a negative 9. And when I divide by 3, I get y equals a negative 3. Therefore, my solution for this system, x is 2 and y is a negative 3. And if I graphed it, that would be the point of intersection for these two lines. Our next example, I have a negative 5c plus 3d equals a negative 16. I have a negative 10c plus d equals a negative 22. Here, I already have both my variables on the left side of the equal sign. They're already in alphabetical order. Now I have to see if my coefficients are opposites for one of my like variables. So here, for my c's, a negative 5 plus negative 10, they are not opposites. For the d's, I have 3 and 1. They are not opposites. But what I can do is create an equivalent system. And that is by multiplying one or both of these equations by a multiple that will get them to be opposites. It doesn't matter which one you use. What I'm going to do is I'm going to multiply my top variable by a negative 2. By doing that, a negative 2 times a negative 5 gives me a positive 10. That would make this opposite, and then I could perform the rest of the procedures to solve the problem. I also could have multiplied my bottom equation by a negative 3 rather than a top by a negative 2, and my d's would have eliminated. But let's continue by multiplying by a negative 2. I'm just going to use the distributive property all through the top equation. So a negative 2 times a negative 5 is 10c. A negative 2 times 3 is going to give me a negative 6d. And a negative 2 times a negative 16 is going to equal 32. And bring down the other equation as is, negative 10c plus d equals a negative 22. Now, I have my c's that have opposite coefficients. So I'll just add these two equations. That's going to give me a negative 5d equals 10. Divide both sides by a negative 5, and d will equal a negative 2. Take the value for d and substitute into one of the original equations. I'm going to use the top one. That's going to give me a negative 5c plus 3 times a negative 2, and that equals a negative 16. Simplifying, I get a negative 5c minus 6 equals a negative 16. This gives me a negative 5c. Add 6 to both sides. That's going to equal a negative 10. Divide by a negative 5. And c equals 2. And our next example, we want to use elimination. Let's get our variables on the left side in alphabetical order. So I'm going to have u minus 4v when I subtract 4v on both sides, and that will leave me 0 on the right side. This next equation already is in alphabetical order with both variables on the left side. 3u plus 2v equals 7. If it was my choice, I would probably solve this by substitution since u is already solved for, but they want us to use elimination. So let's take a look at that method. Here, I look at my coefficients of my u, they are not opposites, and the coefficients of my v are not opposites. So I have to decide which variable I want to eliminate. If I want to eliminate the u, I would multiply the top by a negative 3. That would give me a negative 3u and a positive 3u on the bottom. They would eliminate. Or I could multiply the bottom equation by a positive 2. And that would give me a positive 4 on the bottom and a negative 4 for the top equation, and the v's would eliminate. It's your choice. I'm going to multiply the top by a negative 3. When I do that, I'm going to get a negative 3u plus 12v, and that still equals 0. Bring down my bottom equation, 3u plus 2v equals 7. Now I have my coefficients of my u variable to be opposites, so therefore I'm just going to add these two equations together. The u variable eliminates. That leaves me 14v equals 7. Divide by 14, and v is equal to 1/2. Now I just substitute the value of v into one of the equations. I think probably the easiest is the top one. U equals 4v. V I'll substitute 1/2 in for that value. Therefore, u is equal to 4 times 1 is 4, divided by 2 is 2. So the solution is 2 1/2. My next example, I have 6m plus 12n equals 7, and 8m minus 15n equals a negative 1. This problem is a little bit more difficult because I have to multiply both equations by a number to get my coefficients to be opposites. You just have to choose which one you want to eliminate. I'm going to choose the m's because they seem like they're smaller numbers and I can get them to a multiple a lot easier. So to do that, I can get 6 and 8 to equal 24. So to do that, I'm going to multiply the top equation by a negative 4. That will give me a negative 24m. I'm going to multiply the bottom equation by 3. That will give me a positive 24m. So let's distribute both numbers all the way through. For the top, a negative 4 times 6 is a negative 24m. A negative 4 times 12 is going to give me a negative 48n. And a negative 4 times 7 is going to equal a negative 28. For the bottom equation, 3 times 8 is 24m. 3 times a negative 15 is a negative 45n. And 3 times a negative 1 is going to equal a negative 3. Now that I have opposites in one of my variables, I can just add the equations. When I do that, my m's will eliminate. And when I add a negative 48 plus a negative 45, and that's going to give me a negative 93n equals a negative 31. Divide both sides by a negative 93. And n is going to equal 1/3. Substitute that back into one of my original equations. I'm going to use the top one, 6m plus 12n, but n we know is 1/3, equals 7. That gives me 6m plus 4 equals 7. 6m, subtract 4 on both sides, gives me 3, and m is 1/2. Our next example, we have 2a minus 3b equals a negative 4, and a negative 6a plus 9b equals a negative 15. Here I can get these to be opposites just by multiplying the top by 3. When I do that, that's going to give me 6a minus 9b equals a negative 12. And below, I'm going to just bring the equation over, a negative 6a plus 9b equals a negative 15. Now I add the two equations. The a's eliminate, the b's eliminate. I get 0 equals, and I have a negative 12 plus a negative 15 is a negative 27. Therefore, this statement is false, which means I have no solution. Therefore, if I graphed these two equations, I would end up with parallel lines. And that's why we get a false statement and we have no solution for our system of equations. Next, I have 2x minus y equals 3 and a negative 2x plus y equals a negative 3. Notice here, I have opposites for my variable already, so I'm just going to add. My x's eliminate, my y's eliminate, I get 0, and on the right side, I get 0. Therefore, my statement is true. That tells me that the solutions to this equation is the line itself, because if I graphed each of these equations, they would turn out to be the same line. Therefore, the solution is the line itself. Next, our last example. At Scotto's Pizza, a soda and 2 slices of pizza cost $10.25. A soda and 4 slices of pizza cost $18.75. Find the cost of each item. Well, what I'm going to do is label my items. I'm going to let X equal the cost of pizza per slice. I'm going to have Y equal the cost of soda. Then I set up my two systems. I'm given a soda and 2 slices of pizza. Well, if I have 2 slices of pizza, that's 2x, and a soda plus y is equal to 10.25. Next, I'm given 4 slices of pizza, which is going to give me 4x, and a soda is again y, which equals 18.75. Now I have my system of equations, and all I have to do is get one of my variables to be opposite. So what I'm going to do is I'm going to multiply the top equation by a negative 1, and that will get my y variables to eliminate. That gives me a negative 2x minus y equals a negative 10.25. Bringing over the other equation, 4x plus y is equal to 18.75. When I add, I'm going to get 2x. My y's eliminate because they're opposites, equals a negative 10.25 plus 18.75 is going to give me $8.50. When I divide by 2, that's going to give me x equal to 850 divided by 2 is going to give me 4.25. Now I just substitute back into one of my original equations and solve for y, or the cost of my soda. So 2 times, and I'm going to use the top equation, 425 plus y is equal to 10.25. That gives me 850 plus y is equal to 10.25. Subtract 850 on both sides, and that's going to give me $1.75 for the cost of the soda.